Welcome, everybody. So we've got a few speakers to share their experiences and their ideas with us today. And I'm going to start just with providing a bit of a frame. And Ed, if you can share your screen, the PowerPoint on your screen with us. I just have 2 or 3 slides to put a frame on things. So next slide, please, Ed. So the the frame that I'm putting before you is contained in Manitoba's Road to Resilience Energy Solutions. And you can check it out for yourself. And basically, this document was published in March of this past year, 2022, but it provides an analysis of how it is that we can meet the energy and power challenges of related to the climate change crisis. Next slide, please, Ed. And so really the crux of that challenge is, how do we provide enough power and energy to heat all of our buildings, old and new, and in order to fuel all of our vehicles electrically? That was sort of the challenge that we took on in that Road to Resilience Energy Solutions. Next slide, please. And in order to put numbers to the problem, we went to a publication that Manitoba Hydro put before the Public Utilities Board in 2018, their load forecast document. And it said, okay, because Public Utility Board said, so how would you meet that challenge? Or what was the numbers? And so basically, Hydro's estimate was that if we are going to provide enough power, that is instantaneous power, to heat all of our buildings and charge all of our vehicles when it's 30 below, our peak demand point in time, it would require approximately 8,500 megawatts in addition to the power that Hydro could deliver as of the writing of that document, which was around 6,000 megawatts. And at that time, that year, the most they delivered was something like 4,750. So in other words, the challenge that we put numbers to it, in order to heat our buildings and charge the vehicles, we're going to have to add about 200% more power delivery capability to the electrical system. And another challenge is the energy over the course of the year, which is a little not quite as difficult, but it's still a challenge in that the energy required over the course of the year would be about an additional 100%. So both of these are pretty challenging numbers. I mean, if you look at them on the face of them, holy smokes, how do we do that? Is it possible? Well, next slide, please, Ed. Well, we put forward some scenarios. There's 5 key recommended action areas that we recommended. And you can see in the column second from the right, they're the percent of target power. About 50% of our solution comes from deep retrofits of buildings, making buildings more efficient, making sure the new ones are built efficiently, and some retrofit, deep energy retrofit is done for existing buildings. But a big component of that solution, and that's what we're here for today, is nearly universal adoption of just geothermal heating and cooling for our buildings. And we're proposing that not be done on a building by building basis, but rather as a utility. And in other jurisdictions and in the literature, you might come across thermal energy services as a utility approach to implementation of geothermal type systems. So I didn't want to take up too much of the presentation today, our time today, but hopefully that gives you a sense of why this topic is fundamentally important, because we do have to get away from our reliance on fossil fuels for energy. And electricity is the route that we need to go. And we need to find a scenario that provides sufficient power and energy. Just as a reminder, this document was released in 2020 22 March. And as soon as it was released, we got, even though it was released with a lot of subject matter expert input and a lot of thought, and at that link, you can get an Excel spreadsheet that'll show you all of the detailed calculations that were involved. But we've learned a lot more of the nuances of energy generation and demand over the course of the year. And we have refined our numbers, but we haven't published them yet. So next slide, please, Ed. And that leads me to introduce our primary speaker, who is probably Manitoba's most experienced when it comes to ground source heat systems, and what we vernacularly call in Manitoba geothermal. And with that, I'm just going to say, take it away, Ed.
Hey, thanks, Kurt. As Kurt mentioned, I've learned a lot of ways that don't work over the years, and hopefully we can help avoid some of the mistakes that we've made, that people are prone to make in this industry. One of the things that Kurt mentioned was that to meet our electrical demand and electrical consumption, geothermal plays a very large component of that when you're comparing it to a conventional building with gas boilers, for example, or gas furnaces, and conventional air-cooled chillers. This shows a typical electrical load profile of a building that uses electricity for cooling and gas for heating. There's very little electrical use in the buildings in the winter. A great big high peak demand in the summertime, and a lot of energy consumption. This is on a typical commercial building. If we're looking at switching those to a geothermal system, what happens is that electrical demand reduces pretty significantly by about 30 to 40%. And electricity consumption actually increases a bit, because now we're starting to use electricity in the wintertime to heat the building. So it levels out the electrical load that the utility will see. And as buildings become more efficient, they use less heating in the wintertime, so the demand is going to go down. One of the concerns is that Manitoba Hydro does have a peak demand at this point still in the wintertime, but that is gradually changing. A lot of anywhere further south of us, electrical demand is the highest in the summertime, certainly in Ontario and certainly in Minnesota. So there's a couple of myths about geothermal systems. They're not really well understood. The geothermal industry is maybe about 2% or 3% of the total heating, ventilating, and air conditioning market at this point. First myth is that it's very expensive to install. And there's a design methodology that has been proven over numerous projects that can be reduced pretty significantly with an appropriate design methodology. The second myth is that these things are risky. They overheat, or they get too cold, or they don't provide the energy that you need for the building. And again, a good design methodology, knowing how much energy you're dealing with, is a very critical component of designing these systems. There's another myth, and this is actually a true fact. It does reduce CO2 emissions because you're using electricity a lot more efficiently. And in a province like Manitoba, where most of our power is hydroelectric power, renewable energy, or some wind power, very little fossil fuels, this becomes a very clean source of heating and cooling the building. So just a quick description of what a geothermal system is and what it does. It takes advantage of the temperature of the earth, the energy stored in the earth. And in Winnipeg, that's about 45 degrees Fahrenheit. Across most of Manitoba, that's about 45 degrees Fahrenheit. If you dig down about 10, 15, 20 feet, that's the temperature you're going to find. You're going to get some variation near the surface, but for the most part, even a couple of feet below the surface, it's typically well above freezing. Even though the air temperature can go down to -40 or can get up to about 100 degrees Fahrenheit. And the way we move the energy, take advantage of that energy, is basically build a heat exchanger in the ground. That's typically consists of plastic pipe. Fluid is circulated from the heat pump, picks up, it becomes the temperature of the earth around it, about 45 degrees. It is transferred to the heat pump inside the building, and that heat pump either heats that fluid and rejects heat to the ground, or it cools that fluid, taking heat from the ground. And that heat is transferred, just like through a refrigerator, to the building. If you feel the back of your refrigerator, it's going to be warm, and that heat is coming. The bulk of it's coming from the food that's in the fridge, and some of it is coming from the electricity that's used to run the compressor. The advantage of using the ground as a heat source and a heat sink is that the temperature is much more consistent than the outdoor air temperature. You can see the outdoor air temperature goes down to -30, goes up to about 100 degrees, and the ground temperature in the green stays much more stable. In this case, about 30 to about 80, 85 degrees Fahrenheit, and that depends on how much energy you're rejecting to the ground or extracting from the ground. So the temperature range that the ground source heat pump works at is a much more moderate temperature range than an air source heat pump. Air source heat pumps are a good technology. They quit working at about completely at about -20 degrees Fahrenheit or about 0 degrees C. And as you approach that temperature, they become less and less efficient. And if you're trying to run them at the low temperatures, there's actually times where they run at a coefficient of performance of less than 1 because you have a defrost cycle in that. Even with the low cold temperature heat pumps, air source heat pumps that are out there, they are not really very suitable for this climate. If you're trying, they will not lower electrical demand because they will require electric heat or gas heat backup to make them work when the temperature gets cold. So there's a fundamental difference in designing a conventional system versus designing a ground source heat pump system. And that basically, where that comes from, when you've got a building that's connected to a gas pipeline or to a cooling tower or a fluid cooler or an air-cooled chiller, whatever, you're connected to an infinite energy source. As long as you're paying the utility bills, there's gas coming in that pipeline. As long as you're using water from the utility to evaporate, to get rid of that heat, as long as you pay the utility bill, you've got energy and a heat sink. You can do that as much as you want or as little as you need. But when you're designing a ground source system, you've got a finite piece of dirt that you have to absorb heat from or reject heat to. There's limits to how much heat you can put into that kind of a, basically it's a storage tank. And we're trying to design the systems to operate within the temperature range that the heat pumps, today's heat pumps are designed to operate at. And that's at a maximum temperature of about 85 to 95 degrees Fahrenheit or about 30, 35 degrees C. In the winter, in the summertime, when you're rejecting heat to the ground, if that temperature gets warmer than that, the heat pumps are going to quit working. Same thing in the summertime, or in the wintertime, when you're extracting heat from it, they're designed to take heat from the ground, and they'll quit working if the temperature gets much below about 25 or 30 degrees Fahrenheit, and they work less and less efficiently. So we're typically trying to design the system that the fluid coming into the heat pump is between 30 and about 90, somewhere in that range, Fahrenheit, so about 0 degrees C or up to about 30, 35 degrees C. There's a lot of ways to move heat to and from the ground. In larger commercial buildings, the most common typically is vertical boreholes. Examples of that in Winnipeg are the Alt Hotel, the Hydro Building, a couple places like that, the Nietzsche Commons building up on Main Street. But if you've got the space, pipe can be laid horizontally in the ground like this. School in Steinbach has a system like this, the high school. Systems like this with horizontal directional drilling, a good couple of examples of this. In Winnipeg are the Steinbach Credit Union up in La Jemodier, or the Nurses Pavilion at the University of St. Boniface. You can also transfer heat to and from a lake. If you happen to be near a lake, there's a number of systems installed in residences on Lake of the Woods and in artificial ponds in the countryside around here. There's also a lot of water well systems where you can take water directly from the ground, from the ground, circulate it through a heat pump, extract heat from it or dump heat into it, and that becomes your energy source or heat sink. There's a number of buildings in Winnipeg that have taken advantage of this as well. There's also starting to become a more use of the structures of a building, the piles of a building. Picture on the left is piles being built in a building in downtown Manhattan. They've got 65 piles that are about 120 feet deep, that provide about 40% of the heating for a 250,000 square foot building, and about 30% of the cooling for that building. And that's supplemented by an air source heat pump. Climate is a bit warmer there than it is in Winnipeg, so that works. The ground source is more efficient because the temperature range that they operate at is more moderate. There's systems in Europe where they're building pipe into the tunnel, into the walls of a tunnel for a subway. There's a number of projects that are taking advantage of waste heat from wastewater. So one of the problems in this industry, and this is what we're trying to combat, is that during the feasibility, when somebody is trying to determine whether a geothermal system is appropriate for their building or not, the response they get is often based on rules of thumb. Rules of thumb such as you need about 400 square feet of, you can heat and cool about 400 square feet of building with about 1 ton of equipment. Another building on top of that rule of thumb, often what is suggested is that you need 200 feet of borehole per ton of equipment that's being installed. So what that, it really, the problem is that the size, you're dealing with a mass of dirt. You don't know exactly what the thermal properties are of that dirt. So these rules of thumb don't take that into account. The rules of thumb for 400 square feet per ton, especially with buildings becoming more and more efficient these days, that rule of thumb is basically very misleading. As an example of how misleading that can be, if we've got 3 buildings, we've got a church, we've got a retail store, and an apartment building. Those building loads may be identical. The peak heating and cooling loads may be identical. 140 kilowatts of heating or 480,000 BTUs per hour in cooling, or about 40 tons. And the heating load, 113 kilowatts or about 385,000 BTUs per hour. Those might be identical, and the thermal properties that the ground loop is built underneath them, they may be identical. And that would suggest 40 tons of equipment, 200 feet of drilling, that might be appropriate. In reality, what happens is if you look at the total number right from the bottom of each of these tables, this one, even though the peak load is 480,000 BTUs per hour, how much energy that uses or requires during the year for the church compared to the retail store, these two numbers are quite a bit different. This uses about 3 times as much energy. The cooling system is going to run about 3 times longer to cool that building for the year, the retail store, than it would be used to cool a church. And that's simply because of the way the church is used. That also changes the heating loads, heating requirements for the building. The church will, because the building is not very heavily occupied most of the week, it will require the heat from the ground to heat that building for much of the year, compared to the retail store where the occupants and the lighting and things like that contribute a lot of the heating. Peak loads may be identical, but how much that system is going to run throughout the year is going to be quite a bit different. And then if you take the apartment building, that's somewhere between too big, too small, or just about right. So what that means is that even though these peak loads, peak heating and cooling loads are identical, the amount of energy or how long that system is going to run and how much it's going to extract from the ground over the year or reject to the ground over the year is pretty different with each of these systems. So looking at the 3 in comparison, even though the peak loads are identical, the amount of cooling that the church is going to do per year versus the retail store versus the apartment building is quite a bit different. The heating loads over the year are quite a bit different. How many BTUs or how many kilowatt hours that those buildings are going to need for heating that building is quite a bit different. And then on top of that, you're adding the energy that's used to power the compressor. That has to go somewhere. When you're cooling the building, you're ejecting the heat from the building as well as the heat used that's produced by running the compressor, the electrical energy that goes in on top of that. And in the wintertime, that electrical energy helps contribute some of the heat to the buildings. So the amount of heat you're rejecting to the ground versus how much you're extracting from the ground, you've got to take that into consideration as well. So what that means is that how that ground heat exchanger is going to react with 8,000 feet of borehole, and that's about 40 tons times 200 feet. And that's a common rule of thumb that's used basically across North America. You know, the numbers might vary a little bit in New York State, for example, or in Ontario, or versus Manitoba versus Kansas City, for example. Those numbers may vary a little bit, but those numbers are relatively consistent. And remember that the temperatures that the heat pumps are designed to operate at is about 32 to 40 degrees versus about 85 to 90 degrees Fahrenheit maximum temperature. So what's going to happen in the church, we're extracting so much heat from it that this is going to get dropped down below 30 degrees where it's going to operate very inefficiently. Retail store is going to start getting too warm for the heat pumps to operate efficiently. Whereas the apartment building, it's sitting between about 33 or 34 degrees and up about 70 degrees, well within the efficient operating range of the equipment that's connected to it. Same amount of borehole, same design, same peak loads. These ground heat exchangers are going to act quite a bit differently. What's going to happen over the longer term, the temperature, because we're extracting more heat from it year after year after year, that temperature is gradually going to deteriorate, and it's going to eventually get so cold that the system will quit working. And there have been systems in Manitoba that have quit working because of that. The retail store, because you're rejecting more and more heat to it every year, that's eventually going to get too warm. Whereas the apartment building, it's going to be very stable throughout the life of the building. It's going to change, it's maximum about 70 degrees year after year after year, minimum of about 35 degrees year after year. So what that kind of implies is that even if you make the ground heat exchanger larger, 9,200 or 9,300 feet of drilling instead of 8,000 feet of drilling, that's simply going to delay how long it takes to get to that temperature where the system isn't going to operate. Increasing it again up to, you're only going to delay the inevitable drop in temperature. Same thing with the retail store. Increasing the size of the ground loop from 8,000 feet to 11,000 feet and then to 13,500 feet, all you're doing is delaying the inevitable increase in temperature. And there have been systems that I've seen, even in Manitoba, where the temperature increases over year after year after year, and they quit working. Whereas because the loads are much more balanced, how much heat you're putting into the ground every year versus how much you're extracting, you can actually reduce the size of the ground loop, really optimize the performance of the building so that you can knock 1,000 feet off the ground loop, and it's going to still operate well within the temperature range that those heat pumps are designed to operate at. So even though the ground loops are 37% and 69% larger and 37 and 69% more expensive, with the proper energy balance on the building, you can actually reduce the size of the ground loop, reduce the cost of the ground loop, make the system more efficient all at the same time. So basically what I'm suggesting is that any rules of thumb that you're using, cut off your thumbs. As an example, this is about 100 energy loads from a building, 100,000 square foot building in Winnipeg, where you've got a certain kind of glass specified on it. The peak cooling load, 225 tons, the peak heating load, 157 tons. And if we change this, all we've done is change the kind of glass, change the solar heat gain coefficient, change the U value. We've dropped the heating and cooling loads 100 to 180 tons in cooling. We were at 225. We've knocked quite a few tons off, and we've changed the heating loads a bit as well because the glass is a bit more efficient. So if we look at comparison, we've dropped the cooling loads by close to 20%, dropped the heating loads by the peak loads by about almost 10%, and the annual energy consumption by about 17%. So if you look at the temperature profiles or the energy load profiles, the peak cooling load has dropped pretty significantly. The peak heating load has dropped. The annual energy consumption for heating and the annual energy consumption for cooling have all dropped pretty significantly, simply by changing the kind of glass that's in the building. So what that means on the size of the ground heat exchanger, to maintain a temperature within the reasonable range, 87 degrees maximum, and a minimum of 38.4 degrees, we would need 38,400 feet of drilling. Now, temperatures of the ground heat exchanger is still going to increase a little bit over the next 10 years. Cost of that ground loop at $25 a foot, which is probably pretty common in the Winnipeg area, almost $1 million, $960,000. By changing the glass, you can reduce the amount of borehole that you need from 38,400 to 31,200, down to 78 boreholes. You need less land area, and it's going to operate at a maximum temperature of 85 degrees, a couple degrees cooler, and a minimum of 38.3 degrees, pretty much identical to what the previous one was. And you've knocked off about $180,000 in capital cost. And that can help offset the cost of the better glass on the building. So you can play these kinds of games with a building to really optimize the performance of the building so it works well with the geothermal system. So design methodology, basically looking at understanding the building loads, understanding the geology that you're working with. You can determine what kind of ground heat exchanger is best on that specific site. And you can determine what the energy cost would be. If you've modeled the building accurately, you know how many BTUs or how many kilowatt hours that building is going to use. And you can predict what the energy cost is going to be. And you can also predict how big and how expensive the ground loop is going to be. And look at using the integrated design process. That really can, and working closely with the design team, you can optimize the building, you can optimize the mechanical system to work well with the geothermal system. And with this, I'll pass it off. Mark Mostowy has worked with several buildings over the years that have a geothermal system. And maybe if you have like to make some comments on this, Mark.
Sure. Yeah. Hi, everybody. I think my role here today was to kind of give you some of the experience that I've had being a facility manager, not part of design or install at the time, just happening to inherit a geothermal system. So I've had two separate organizations that I've worked with. The first one was with IKEA in Winnipeg, obviously retail store. The energy load there was obviously for basically a warehouse throughout, even though you know, there's different settings in there in different areas. I think my biggest concern to hand out here is really talking about install. In this organization, the install was I can't say anything different other than it was really poor. We've had pipes cracking right at the heat pump, just with the energy being expensed and having variable, the variable speeds going through it. So the piping was cracking throughout the warehouse. There was piping cracking that was in variable spots in damaging hundreds of thousands of dollars of materials in the building. Also with the install, there seemed to be no shut-off valves to isolate certain parts of the building. So that required every time that there was a leak, and of course we had some contractors that came in and they would start putting in these shut-off valves, but you'd have to drain that whole system through the whole store and then store that glycol and until things were repaired and fixed. And this happened. I wasn't there too long. I was there a few years, and that just continued. And IKEA worked very hard at getting that the solutions based and to get the proper install of piping and stuff like that to be done. Then I left IKEA and then came to Steinbach Credit Union, where I currently am. This building here is in Steinbach. It's our head office and branch. Apparently, again, so not being involved from the beginning when it was all designed and the building was built, I was told that there was lots of issues with, again, the install. There was a understanding that bigger was better, but not necessarily when not necessarily when you're dealing with certain pressure types. So as a rural firefighter, I can tell you that trickle of water going through a 3-inch hose 100 feet isn't really going to do much at the end of that 100 feet. And I would guess the same thing with a geothermal system. If you don't have if you're installing, your design is the piping is too big for what you need or too small, I guess, it's not going to work that great. So that was kind of the problems that I think existed here. We, as well as IKEA, and this building is an open loop system. So again, a little different than the next building we'll talk about, but the open loop system, we've had, our boilers were on. So there was some not, the efficiency wasn't as I expected, based on the fact that, our colder winters and stuff. So in Steinbach, our boilers are on pretty much the winter. We turn them on end of November, and they're on till about March. Their next building, our Lajimodi branch, I know Ed brought it up earlier, is a closed loop system. So that's a little different. So the design is again different, and the install, I believe, was a lot better in this building, from my knowledge. There's a lot more efficiency in this building, and again, is design and closed loop system. We turn our boilers on in this building for about 2 to 4 weeks. And that's it. It depends on how cold the winter is. So far this year, we haven't turned our boilers on. We've run strictly off geothermal. So again, I just think when you have one of the things I wanted to mention, when you have your open loop system, you're reporting to the province of Manitoba here. I don't know if that's the same everywhere else. We're reporting our water usage and temperature on an annual basis. And with our closed loop system, we do not report to the province. So there's no reporting schedule there. Other than that, I just think that, like I say, I think with the SU design as well, and the energy loads are for office buildings, again, which were totally different than dealing with IKEA building, which is more a warehouse type design. Definitely a lot of efficiencies here with Steinbach. And again, we've looked into and have talked about as an organization to even expense some of that other energies with the geo system by possibly heating the front walkways. So we heat those in the wintertime so that they heat and dry and they don't become slippery and stuff. And it's just different ways that we are looking at possibly moving on as an organization. That's it.
A couple of quick comments I wouldn't mind making on here is that this system has been monitored for the last 2 years. The temperature range, the maximum we've seen on there is about 87 or 88 degrees Fahrenheit, or about just over 30 degrees C. And the minimum temperature it's seen is about just over 40 degrees Fahrenheit, or about 5 degrees Celsius. So that's been pretty consistent right from day one when it's built about, I guess about 14 years ago now. The interesting thing about this is that the amount of cooling that this system has been doing on an annual basis for the last 2 years is significantly higher than the amount of heating that's required in the building. The building itself is a very energy efficient building, and it requires a lot less heating than it requires cooling. Okay, John, if you want to take it away from here. John is with Otter Tail Power, has been working with the utility there for about 6 or 7 years now.
Thank you, Ed. Just a little bit of background on my role at Otter Tail. A little bit of background on Otter Tail first, maybe. We're one of the smallest investor-owned utilities operating in the United States. And we serve about 145,000 customers throughout Minnesota, North Dakota, and South Dakota. In the states of Minnesota and South Dakota, we provide a number of energy efficiency programs. That's a legislative requirement. Plus, we go through a process of integrated resource planning that showed energy efficiency is really one of the most cost-effective ways for us to, in the long run, meet customer demand for electricity. So in the capacity of managing and developing these programs at Otter Tail, a couple of the different ones we offer are what we call the Integrated Design Plus program, and then direct cash rebate incentives for customers installing geothermal heating systems. And anecdotally, what we were seeing in bringing that design assistance program to our customers is a lot of reluctance on the part of design teams out there to really adopt geothermal in building designs, and a lot of reluctance on the part of building owners to install geothermal, primarily out of beliefs that the costs are exorbitantly high, there's no payback, and one or two cases of performance issues. Sort of as a strategy to counteract what we were seeing out there anecdotally, we started working with Ed on a number of different strategies. And through that Integrated Design Plus program, we've always offered energy modeling in terms of the building. How is this building going to react if we change these windows to something more energy efficient, or we add more insulation in the roof? When we brought Ed in, we were able to walk through an iterative process between the building and the loop field. And going through that, what we found is that we were able to, on average, probably reduce the loop field installation cost by a factor of about 40%. So all of a sudden, we start factoring in the proper design and lowering the loop field costs that way. And in addition, Otter Tail's cash rebate incentives for customers installing geothermal, and in some cases, even federal tax credits. And we're seeing some real changes. And you can see here on the slide that Ed's pulled up, prior to really getting this effort off the ground, we had approached a number of customers and had only 2 projects actually go geothermal. And my belief is those were going to go no matter what. Once we got this up and running through this design process, we were able to convert what probably would not have gone geothermal. About 8 of them ended up going with geothermal. And Ed, I think you can probably explain then the next step, your personal experience from some of these design teams you worked with through our program. I believe they started then in territories outside those that we serve. Those engineering firms started recommending geothermal to their own clients.
Yeah, basically what happened is that some of the engineering firms that we had the opportunity to work with on some of the buildings within Otter Tail territory had actually started recommending geothermal systems. Once they understood the methodology and understood the design process, they recommended it. They just wanted a little bit of review on their design to make sure that they were staying, basically painting between the lines, making sure that the systems are going to work. So once they understood the process and understood the methodology, they became a lot more comfortable with suggesting that a geothermal system might be appropriate for their other clients as well. So basically what I'm suggesting is that with a well-designed system, you're going to offer a good solid return on the investment in a lot of cases. Also, it'll improve the performance, the long-term performance of the system, and reduce the risk, mitigate any kind of risk that you might see with it. And it will still give you the CO2 reductions that you're looking for. And these systems do work virtually anywhere in the world. I've seen systems designed in Siberia and permafrost. I've seen systems designed in Kerala province in India, where the ground temperature is 80 degrees. And these systems can work, and they can work in virtually anywhere. And they can reduce energy consumption and energy peak electrical demand pretty significantly compared to a conventional system, where you've got air-cooled air conditioning and gas boilers or whatever. So I guess we'll leave it there for any questions that you might have, or certainly happy to chat about any of this.
So we've got a few questions that have come in already. So the first question is, what electrical/mechanical space will be required for heating/cooling a building of 10,000 square feet?
That could actually be less than a conventional system. It depends on how the system is designed. There are systems in that size of a building. I actually looked at one just this morning, about 12,000 square feet, and the amount of mechanical room space was required just for piping to come in from the ground heat exchanger and a circulating pump, and that was about it. The heat pumps themselves were in this particular building were mounted in the ceiling, and taking up no mechanical room space. The Steinbeck Credit Union, on the other hand, on Lagimodia has several mechanical rooms that would be similar in size to a conventional system mechanical room. So it really doesn't take any more space. In some cases, can take less space.
Great, thank you. So our next question is, after the building is built, how do ground source heat pumps designs accommodate changes in occupancy or demand in buildings they serve?
That's a really good question. That's one of the reasons that we started monitoring the system on Lagimodia. And with the design software that's available right now that we've been using for the last 15 years, it's possible to, if you know what the energy loads are on an hour-by-hour basis, if you've done a good energy model, you can predict what the temperature of that ground loop is going to be over the next year, next 5, next 10 years. And what we're doing on that building is that there's an energy meter on the ground heat exchanger that measures how many BTUs you're taking from the ground or dumping into the ground. And with that information, we can feed that into the software and predict if that temperature of that ground loop is going to get warmer and warmer and warmer over time, or get colder over time. And then we can make adjustments to the system. And that will take into account changes in climate from changes in weather from one year to another, changes in climate over the next 10, 20 years, changes in occupants of the building, changes in lighting upgrades, changes in glass upgrades. You can take all of that into consideration. If you know how much energy you're dealing with, then you can deal with that within the system and adjust it accordingly. Keep it up, really optimize the long-term performance of the system.
So the next question, oh, go ahead.
One thing I'd like to add to my last comment is that in my own house, I put my ground heat exchanger in about 1992, I think it was. And over the years, because houses in our climate tend to do a lot more heating, unless you've got a passive house, they do a lot more heating than they do cooling. And over the years, the temperature of my ground loop dropped down to about 23.5 degrees. And about 4 years ago, I installed a small solar thermal panel on the roof that it's about 8 foot by 12 foot, simple plastic pool heater kind of a panel. And all summer long as there's no snow cover on it, it dumps a bit of heat into the ground. And this year, my temperature right now, I just checked it this morning, was about 33 degrees Fahrenheit, well above, about 10 degrees above what it was 3 or 4 years ago. So that you can use the ground as a storage tank. You can manage the temperature of the ground loop if you're monitoring it.
Laura, just to expand off of Ed's point, in applying his principles in the real world, we're not only able to reduce those loop field sizes and costs, but when he goes through that iterative process of matching or tweaking a building design to reflect how that loop field is going to react, it allows us to look out 20, 30, or 40 years and model the loop field temperature. So we at least know up front that we've modeled it and we've shown that it's not going to do what that church did or what that retail store modeled out. And it's going to be more stable over the long run and perform better.
Next question is, in Manitoba, is there an approved list of qualified installers that are certified? Also, are there recommended installers here in Manitoba? Just curious. Thanks.
There are a couple of installers that do a lot of geothermal systems. There are about 20 or 30 listed on the Manitoba Geothermal Energy Association, but a lot of them haven't been doing a lot of installations. There simply hasn't been a lot of call for geothermal systems. And to put it bluntly, there have been poor designs in the system in Manitoba that people refer to. Mark had mentioned a couple of them where systems are maybe oversized, or maybe the installation hasn't been as good as it could be. That can help. That doesn't help the reputation of the industry, and that just expands on the myths that there are. If the systems are designed properly, and that means that you need to do a good energy model of the building to start with, know how much energy you're dealing with, know what kind of ground conditions you're dealing with, and you can basically design the system that it's not difficult. It's different than what most mechanical designers are used to doing. You don't have to design a gas pipeline for a gas well and a gas pipeline for your building when you've got connected to a gas line. You do for a ground source system. You have to design that portion of it. So there is some extra work involved in there. It's like I said, it's not difficult. It's different.
Okay, so what are the opportunities for ground source heat pumps in urban residential applications? More so narrow infill lots.
That is a bit of a challenge, and this is one of the things that Kurt mentioned earlier, what it is possible to do. One of the problems in that kind of a situation, to drill a vertical borehole on a small city lot, especially on an infill lot, there isn't often a lot of room, and that can become challenging. But what can be done, we've done a number of feasibility studies. We did one for the city of Woodstock, Ontario, about 4 or 5 years ago. Is it possible to build a geothermal utility on a citywide basis? And what we found at that point, technically very easy to do, very possible. And it would save the homeowners some cost on it. They would connect up to a pipe going in front of their home, very much like a gas pipeline, except it's taking liquid from the ground. The boreholes or the ground heat exchanger that pipe is connected to might be in the schoolyard across the street, or it might be in the park down the street, or it might be in the boulevard up and down the street. So that gives you the room to do that. And if you connect a bunch of buildings to the same ground heat exchanger, it works really well if you've got a system. For example, we did a study for the area around the Dakota Community Center a few years back, and there's enough heat that's being rejected through the cooling tower of the ice plant of the Dakota rink, and they've got 2 ice rinks, to provide the heating and cooling for the school next door, which is about 60,000 square feet, the library next door, 15,000 square feet, the community center itself, which is about 25,000 square feet, plus the ice rinks, plus the personal care home down the street, about 80,000 square feet, plus about 110 homes that are surrounding the field around there. And the size of the ground loop actually is, the more balanced the loads are, the smaller the ground heat exchanger has to be, the less expensive it is to install. So there are definitely opportunities in that kind of a situation where you could have 5 or 10 or 15 or 20 homeowners up and down the street or down a city block connecting up to the same system. It's going to work a little bit better if there's a heat source, or like a commercial store or something like that, or like the IKEA store, for example, is going to reject more heat to the ground than it's going to take from it. So a data center, for example, can act as an energy source for a whole community. So those are the kinds of things that you can do. We're looking for those kinds of opportunities, which makes it more cost effective. And again, it gets rid of the burning fossil fuels and uses electricity a lot more efficiently.
Okay, so what energy simulation program do you use to test the designs?
Say that again, sorry.
What's the energy simulation program that you use to test the designs?
We're using energy modeling software such, we use Train Trace, but there's other ones like IES or Carrier HAP or any one of those, eQuest, can all produce the energy loads that we need to simulate what the building is going to need for heating and for cooling, how many BTUs every hour. Then we use software. There's a number of different software packages available for designing the ground heat exchanger. We use GLD, but there's other ones called LoopLink Pro or GLE Pro or GLHE Pro, and there's a few of them out there that are available. For a large district system, we've started using a program called Trinsis. It's a transient, can't even remember what it all stands for, a simulation software of some sort, where you can feed the loads from the energy modeling software from a dozen or 20 or 30 buildings into the software, and you can feed the design of the ground heat exchanger, and it can also simulate what that system would do if you added solar thermal to it, or combined heat and power, or a snow melt system if you need to get rid of heat, any number of things. There's software out there that can do all of this.
Thank you. So is it possible to design a system that won't fail over time?
Yes, period. A good example would be a Steinbach Credit Union up in La Jamodia. It's been running well within, it was designed to operate between 35 and 85, and that's pretty much where it's been. There's been some variation. On a really, really hot summer, it might get up to 90. On a really, really cold winter, it might drop down to 30.
Okay, so in regards to return on investment, how many years to break even, or what is a more appropriate ROI metric? A lot of that is going to depend on what the cost is of natural gas or other fossil fuel that you might be using versus the cost of electricity. And typically what we are seeing with a well-designed system in Winnipeg, probably between 5 and 10 years would be a simple payback. Return on investment, that's probably about 15, 20%, 10 to 20% for sure, is quite common if the system is well designed.
if a system is inappropriately designed. And that's what the clients that John Fabre talked about. They were looking at long paybacks, and because with looking at accurate energy modeling of the building, iterative energy models of the building, what happens if you change the glass, what happens if you change the ventilation strategy, those kinds of things, what happens if you change the lighting system in there, those kinds of things. You can actually manipulate the building heating and cooling loads to balance the loads, and that as John mentioned, was able to reduce the cost of the ground heat exchanger, which is about what the incremental cost is of a geothermal system, can reduce the incremental cost by about 40%. So it can be done. It's got to be, you've got to understand how much energy you're dealing with and what kind of ground conditions you're dealing with and what you can do on a specific site. That's the most cost-effective way of approaching it. There are a lot of different ways of putting pipe in the ground, whether it's horizontal drilling or horizontal excavation or vertical drilling or a well water system. They all work. And but what is the most effective system on that specific site? It's not a kind of a system where you can order a ground loop from a catalog. It just doesn't happen. It's not possible. You've got to actually design it.
Do you have anything that you want to expand on about telling clients about the payback period, since that is one of the myths?
We know that for sure, that the cost of natural gas is going to double or triple in the next number of years with the carbon tax. So the cost might be lower with natural gas right now. That's changing. And with the political situation around the world, who knows where that's going to go. Cost of electricity in Manitoba looks like it's going to be fairly stable for the next number of years with minimal increases. So the payback's going to get better. Designing systems that the heat pumps themselves, we're finding more and more ways of supplementing the heating system. Like on my house, for example, we can reduce the size of the ground heat exchanger in a typical house with the modeling that we've done by about 40 to 50% if we can add a solar thermal component to it. So in other words, to balance the loads, add a bit of solar thermal, we can reduce the overall cost of the system and make it more efficient and ensure that it's going to operate efficiently for the life of the building. One of the systems that we looked at in Minnesota recently was where we can look at changing the properties of the glass that are in the is in the building by putting a small electric current into it and changing the amount of solar gains that can come into the building by darkening or lightening the glass. So that way you can actually manage the temperature of the ground heat exchanger over time if you're monitoring the system and saying basically if we see that the ground heat exchanger is trending to become too warm over the next few years, we'll send a signal to the glass control system and say, hey, you've got to darken the glass a little bit for the next couple of months and reduce the cooling loads, increase the heating loads. That's the kind of thing that you can start doing.
So what is the method used to determine the energy characteristics of the ground?
The type of ground that you're installing the ground heat exchanger, you're measuring the thermal conductivity of the ground, how much heat you can transfer through, dump into the ground and pull from the ground. You can measure the speed at which you can dump the heat into the ground by measuring the diffusivity. You know what the temperature is of the ground, and then you also have to look at how are the contractors going to get that pipe into the ground that you're trying to get it into. And you find in some areas, for example, that you may hit a very difficult drilling condition at a certain depth, might be 250 feet or whatever it is. Then you can redesign the ground heat exchanger to accommodate those kind of changes if at all possible. And look at supplementary heating or cooling devices, such as a fluid cooler, or in some cases, a boiler of some sort or another to supplement it on those really bad peak days.
Okay, existing residential context, 2-story, 4 bedrooms. How much landscape is needed to install? Are there systems designed for shoehorning?
For shoehorning, okay, getting into a real small space is what I'm guessing is referring to. We've looked at houses in Winnipeg, for example, where you might need 1 or 2 boreholes that might be spaced 10 or 15 or 20 feet, probably about 15 or 20 feet apart. And we can drill comfortably up to about 400 feet in Winnipeg. That would accommodate Most houses, a typical house, if the house, one of the things that we've tried to do, the other thing that we're starting to do as well is there are piles that are drilled into the ground, steel pipe with a drill bit at the end of it, and they drill into the ground about 40, 50, 60 feet in Winnipeg till they hit limestone. And it's possible to put pipe in the ground in the supporting structure for the building. And there's a couple of houses going up this coming summer that have about 37 piles under the building like that. They're about 55 feet deep. And with a few small tweaks on how much insulation is put on the building, those piles themselves can meet the heating and cooling loads of the building. So if you're building a new building, that kind of thing can be done. And then you don't need any additional land space.
Okay, so how long have heat pumps typically been lasting before needing total replacement? And how does that affect the overall payback period?
The cost, like I installed my first heat pump in my house in 1992, and I replaced it after about 23 years, so about 2015. And I simply took the old heat pump out and put a new heat pump onto the same ground loop. So I didn't have to build a new ground loop. So I'm looking at just the cost of equipment, which is probably equivalent to standard gas furnace and air conditioner. And a lot from what I've been told by contractors that install both air source and ground source systems, the equipment itself is less expensive for a ground source system than it is for an air source equipment.
Okay, so in the church example, how does the design deal with the long-term failure that you described, drawing heat out of the ground over time?
What we would do in that kind of situation is try and find ways of, first of all, reducing the cooling load or the heating load as much as possible. And that might be putting in better windows, better insulation on the walls. And then if you can't do that and do enough of that on the building, then you would consider maybe putting on solar thermal panels on the roof to supplement the capacity of the ground, dump heat into the ground during the summertime or during the winter as well. So basically, some ways of balancing the loads one way or another, whether that's within the building itself, with the building design, looking at an energy recovery ventilation system on a building like that might make a big difference. But we'd look at, and that's why we do the energy modeling. We'll often create half a dozen or a dozen different energy models for the same building to see what happens if we do this, that, or the other thing.
Okay, so what's most cost-effective regarding renewable energy? Solar panels, geothermal systems, and windmills.
Geothermal systems help leverage what you can do with a solar panel and with wind power. Because if you're putting in like a typical house in Manitoba, if it was on electric heat, would draw maybe 10 kilowatts of electricity. That's how much a big furnace you would need. And if you install a geothermal system, you would need it would draw about 2.5 kilowatts. So the size of a solar panel you need for an electrically heated home would be 4 times larger than you would need for a heat pump, home heated with a heat pump. So it helps make the cost of the PV system that you need for your home a lot less. Or if you've got a wind generator or you want to use wind power, you use a lot less of it. So a geothermal system really is kind of is one of those things that leverages all of the other renewable technologies, makes them all look a lot better, and it makes the ground source system look a lot better, because then you can start, like I'm putting a PV cell system on my home, and it'll provide about half of the power for an electrically heated home. And my place isn't in a very good orientation for solar panels to start with, so.
Alas. So how does high water table affect the outcome of the geothermal system?
Depends on where you're at, but if you're in a lot of cases, moisture in the ground is going to make it the conductivity of the ground a bit better. And if you've got groundwater movement in the ground, like in Winnipeg, for example, if you're drilling to 300 or 400 feet, there is groundwater movement in the fractures and the cracks in the limestone below us. And that will help bring additional new energy to your boreholes. Or if you're putting a lot of heat into the ground, it'll drag that excess heat away. It'll help improve the performance of the system.
Okay, district geothermal heating and cooling would be amazing as a way to reduce energy consumption in the entire city. That was just a comment, not a question. Sorry. As we know, humans have been changing the ecosystems with buildings, transportation, and their emissions. Now, with the concept of geothermal, they are starting tapping into below ground ecosystems. Those were in balance. What would your response be to this? And what are the proactive measures geothermal systems are taking into consideration?
So is that basically wondering about the environmental impact of raising the temperature or reducing the temperature of the ground?
Yeah, and I think just generally changing the ecosystems below ground.
Okay, it is changing the temperature of the ground. If a well-designed system is going to stay above freezing and even in Winnipeg, and it's going to stay probably below about 85 degrees. Haven't seen any, I've never seen any reports that really show any adverse effects of changing the temperature of the ground. Natural ground temperatures across the world are anywhere below, where you've got permafrost, you've got a bit more extreme temperatures in natural conditions than we're doing with the ground itself. There's ground temperatures in India that I've run into that are about 82 degrees. So there's the systems are whatever's in there is potentially, hopefully, going to adapt to it. We're looking at moderate changes in the temperature, and we're affecting the area within a few feet of the borehole. So we're not affecting a huge amount of area. So, but like I said, I haven't seen any really reports showing any adverse effects. There's a system in Okotoks, just south of Calgary, that they use solar thermal energy to raise the temperature of the ground up to about 160 degrees Fahrenheit. I would have some concerns in that kind of a situation. But we're with the heat pump, we're operating under fairly moderate temperature ranges.
Okay, so Andy is a homeowner that wants to upgrade to ground geothermal from electric furnace, and also install solar panels. What would your advice be?
Look at first, if it's a new building, make sure that the building is going to be built as efficiently as possible to start with. Make sure that the infiltration is reduced and everything else. Insulation values are where they should be, or even a bit better. That's going to reduce the size and the cost of the ground heat exchanger that you need. It's going to reduce the imbalance between the heating and cooling loads that we see in a typical house in Manitoba. Look pretty closely at what kind of glass you're putting in the building. All of those kinds of things make a difference. And if you're looking at solar PV as well, again, you obviously want to look at the efficiency of the appliances and things like that you're using, so you can minimize the electrical consumption. And if you can minimize the size of the heat pump that you need, that's going to certainly help. It'll help leverage how much you can do with solar panels.
So Jim is looking for super clarity. What comes first, better building envelope or geothermal heat pump?
Better building envelope, period.
Okay, is there a requirement to survey the ground loop system? In a potential future where with significant geothermal uptake, would neighboring systems be required to identify piping locations for setbacks and proximity monitoring?
Yeah, you should know where the ground heat exchanger is on any building. I have seen systems where that wasn't taken into account when they built the ground heat exchanger, and 5 years later, a backhoe digs up the ground loop. That doesn't help the operation of the system. It costs a lot of repairs. So yeah, you do need to know where the pipes are, and the contractor that's installing it should be able to tell you where each borehole is, and you should be able to locate it whenever you need to.
Okay, so in a whole neighborhood being put on geothermal, what are the frost line impacts of that mass geothermal?
If the system is well designed and you've got the loads balanced, there should be very little impact.
Okay. How can you describe the maintenance side of heat pumps? Is it hard to maintain it? Glycol changes periodically, pump drives, maintenance, etc.
The heat pump I put in my house, I had to replace the blower motor after about 20 years and replace the heat pump in about 3 years after that, because it was either replace the compressor or upgrade to a better, more efficient heat pump that was available. If the system is well designed and if you're feeding the right water flow within the temperature range that it's designed to operate at, and it's got the right airflow that it's designed to operate at, it's basically like a refrigerator. It's going to last 20, 25 years. It's going to last longer than your air source heat pump or an air conditioner or a gas furnace for a couple of reasons. One is that an air source heat pump or a standard air conditioner is exposed to the outdoor environment where there's a lot of dust and all kinds of things like that that are going to clog up the coil. It's going to have a lifespan of 15 to 18 years. Ground source heat pump, a number of studies have shown 20 to 25 years for the life of the equipment. Gas furnaces, because they're operating with very high temperatures on the heat exchanger, a flame, which is heating the heat exchanger, they're exposed to very high extreme temperature ranges, which is very hard to deal with any material to deal with. And it's going to last 10, 15, 20 years.
Okay, so is there a need to have a backup heating source in case the heat pump will generate below the desired temperature?
My system, I've got electric auxiliary on mine, about 7 kilowatts of electric auxiliary. Last year and the year before, this winter, it hasn't come on at all. The year before, it didn't come on at all. The year before that, 3 winters ago, it came on for a total of about 30 minutes on a day that we had about 2 week spread of a stretch of minus 30, minus 40 degree temperatures, if you remember that. And it came on probably 10 minutes at a time for 3 or 4 times. And it's quite possible that the Steinbeck Credit Union, I think for the most part, runs without any auxiliary heat. I think Mark said it runs this winter, it hasn't at all. It's not a bad idea if you've got a very mission critical kind of situation, then you probably want a different fuel on there as well as electricity. It depends on your situation, but you can't design a system without that.
Well, everyone, thank you so much for your time here today. Thank you everyone who shared their expertise, who shared their questions, and who shared their time. Really, really appreciate it. I hope you have a great rest of your day. Keep an eye on SBM's socials and on the newsletter for what's coming next. Thank you so much, everybody.
Thank you all. Good to meet you.
Okay, take care.